Okay, so we all saw that wallpaper thing, which you're going to produce a version of for your assignment. So in this session now, I'm going to do a similar programming exercise and talk you through the various ways we think about it and how we arrive at the final program. But what we're going to do, rather than do that wallpaper one, we're going to do a similar one which employs similar things. We're going to do an orbiting motif. So we're going to have some kind of shape, and we're going to send it orbiting around a center. So we're going to produce an animation which has this shape orbiting around some central point. Okay, central there, but center over there. And okay, so obviously, yeah, okay. And we're going to use various two-dimensional transformations to do that. Then maybe we can introduce some new things to it to make it a bit more sophisticated. We, as well as getting the motif going around orbiting around some fixed point, we'll make it rotate in place as it goes. So the motif will be spinning around its own center. So we'll have a center point for the motif, while having it spinning around its own center while it rotates, while it orbits around the main central point. Okay. And then maybe we'll maybe also get it to do this pulsating thing. So as well as rotating around its own center while it's orbiting around the center, we'll maybe get it to pulsate, grow in shape, and shrink down smoothly as it rotates around. So we'll get it to pulsate out and then get down really small and shrink down. All the while spinning around its own center and orbiting around. Okay. I've got some skeleton code ready. We'll have a look at that, and then we'll add the appropriate things into it to carry out this. Okay. But first of all, the basic MATLAB tools we're going to use, so basic aspects of the program, we'll define a motif as a polygon defined by a set of vertices. So I'll have a basic polygon, and the basic polygon I'm going to use for this one is this kind of a shape here. That's the shape I'm going to use for this example. So it's just a collection of vertices, and this kind of star-like shape I'm going to use. Okay, it's just a bunch of vertices and then just straight lines joining the vertices. And this is the shape that I'm going to make orbit around the center and rotate around itself and expand out and expand out. So we'll think of it, we'll have a basic motif then like this, centered at the origin. Centered in some way at the origin. So that's our basic motif. And then to produce each frame of this animation I'm going to do, for each frame of the animation, I want to pick up this motif, which is centered at the origin and has some standard size, and I want to put it in the appropriate place for that frame of the rotation. So for a general frame in the middle of the animation, I'll have to do a number of things. I'll have to rotate the basic motif a certain amount around its own center. I'll then have to shrink or expand it a certain amount. And finally, I'll have to translate it away from the origin. So we'll use this as the origin. The basic motif initially is centered at the origin. So I want to rotate it around its own center, shrink or expand it as appropriate, and then translate it to the appropriate point on the orbit circle. Okay. There's a number of different transformations. I'm going to rotate the thing around its center, rotate it around the origin. shrink or expand it, and then finally translate it to the correct point around the axis, around the circular orbital path. Okay. So for each frame of the animation, I want to rotate, scale, so that could be expand or shrink, scaling operation, rotate, scale, and translate the motif to the correct place, to the correct location on the orbital. Let's say we're using a circle for the orbital, on the orbital circle. Now, how is the motif going to be stored? We'll store the basic motif. We'll store the basic motif as an array. We'll give the name of the program. So the array is going to be of homogeneous vertex coordinates. So we're going to have x1, y1, 1, x2, y2, 1, as far as xn, yn, 1. So it's a 3 by n matrix, 3 rows and n columns. Each column is the homogeneous coordinates of a point, of a vertex of the motif. So this is v1, v2, and these vertices should be in order as you go around. And then there's a MATLAB command you'll use, which just joins all the vertices up with lines to produce a polygon. Okay. So this is how we'll store the coordinates of the motif. Okay. And then to produce new coordinates, that's the basic motif we'll store at the start. That's the ones of standard size, center at the origin. To get the new coordinates for a motif that's placed in the correct position and maybe rotated and maybe scaled, we'll multiply this matrix by the appropriate transformation matrices. So to produce new coordinates, we multiply this array by a transformation matrix. So we'll have some transformation matrix A, which will multiply this. So A is multiplying into the coordinate, the motif coordinate matrix. And this will produce a new set of columns. Okay. Let's call it x prime 1, y prime 1, x prime 2, y prime 2, 1, and so on. Xn prime, yn prime 1. So these coordinates here, after you've multiplied it by the appropriate matrix, or maybe this transformation matrix might itself be a product of a few different transformation matrices. You keep multiplying the coordinates by the appropriate transformation matrix until you get the final set of coordinates, which you then want to plot for that particular frame. So these final coordinates here will be the coordinates of the correct motif at some position, some size, some rotation around the orbital path. So that's all the low-level stuff that we're going to do. And for actually drawing each frame, we'll use the fill command. Fill command. So the fill command is you give it a load of x coordinates, you give it a load of y coordinates, and it just joins each vertex to the next one by a straight line. Okay. So if I specify, give it this collection of x and y coordinates of these points, the fill command will actually draw this polygon formed by those vertices. Okay. Now later on in the second term with John and Shiak, you'll actually be, drawing a point between two lines is a non-trivial exercise, of course, because when you think about it, I mean, what's the computer screen really, or what's the computer display really? If you zoom in on the computer display, what you see is just a grid of pixels, in some sense. Okay. It's just a rectangular grid of pixels. So really, the only thing the computer can do is switch on or switch off. Just talking about black and white. Is just switch on or switch off each pixel. So it's a non-trivial problem given 2 points in the plane, how to draw a line between them. Because all the computer can do is light up this pixel or light up that pixel. So how do you decide which pixels you light up to draw a line? So that's one of the graphics algorithms that John Shiak will be doing with you in the second term. But we're not going to worry about that for the moment. We're just going to make use of the MATLAB fill command to do that. But the low-level stuff we're going to do is the specification of the motif, and then the necessary translations to produce each frame of the animation. Okay. So any questions at this point? Send around the Everybody finish with that page? Yeah. No? So I've got a skeleton file set up, which we're going to start working with now. And it's very similar to the skeleton file, that's up on Moodle for your wallpaper problem. Okay. First of all, we need to figure out the correct coordinates for my basic motif. So here's the basic motif. I'm going to have these points here, and these points here further out along the axes. I'm going to talk about this star shape here. That's a kind of a very bad sketch, but let's say I'm going to use these points at distance 3 along. And these points are going to be at distance 1 along. Okay, so I'm going to use these 4 points, which are on the vertices of the unit square, and then another 4 points lying on each of the 4 axes, which are at position 3. So those are the x and y coordinates of these points as I go around my motif. So I'll call this V1, this one V2, V3, and so on as we go all the way around. So we'll want to input those into our program as well. Okay, so my coordinate matrix will look like, remember I'm using homogeneous coordinates, so all these 2-dimensional points, they all have third coordinate 1. Okay, so we're using the third homogeneous coordinate 1 just so we can make use of, so we can carry out translations using a translation matrix. So for instance, the first column is going to look like 3, 0, 1. Second column is going to be 1, 1, 0. Sorry, 1, 1, 1. So that's the point V2. The point V3 is 0, 3, 1. This point here is minus 1, 1, 1. And we've got minus 3, 0, 1. And minus 1, minus 1, 1. Then 0, minus 3, 1. And lastly, 1, minus 1, 1. It's got 8 coordinates. Yep, 4 plus 4. 8 coordinates, and those are the homogeneous vertices. So that's the basic motif array. Okay. I'll switch over to the MATLAB now because I'll be inputting that shortly into the thing. But it's just the coordinates you get, and you go around that polygon and pick up those vertices. Oh, sure. Just log back into this. Do that, do that. Okay, so, well, the first thing is I'll just briefly introduce you to the skeleton code for the wallpaper example. So this is what's displaying here is the M file that's up on Moodle. The structure of it is there's a main function which is called dynamic wallpaper. So that holds the main script or the main program that produces the animation. And there are some extra functions. Just skipping over that for the moment, looking down at the bottom, there are 3 little functions down the bottom. One called rot matrix, one called trans matrix, and one called scale matrix. So these are little functions that return the appropriate transformation matrix for the appropriate transformation in homogeneous coordinates. So the rotation matrix is the rotation matrix by theta radians anti-clockwise about the origin. Trans matrix takes 2 inputs, x and y. So those are going to be the x and y coordinates of the translation vector. And scale matrix just takes 1 parameter, r, which is just a scaling parameter. So if it's between 0 and 1, it's a shrinking transformation. If it's greater than 1, it's a expanding scaling. Now, in the skeleton code, those functions are just set to return the 3x3 identity matrix. See, the rot matrix function returns a matrix R, but R is at the moment just set as I3 3x3 identity matrix. So the first thing you'll have to do, although I'm going to do it for you now in the other orbiting one, is we'll have to get the correct definitions for the transformation matrices. So those are our kind of sub-functions that the main function, the main script, the main program is going to use. So let's just look at what's in the wallpaper skeleton file. There's lots of comments in green there which explain the different aspects of the program and give you tips on what you're going to do. So there's an array here, motif coordinates. And this is where you're going to specify your basic motifs. This is supposed to be a motif centered at the origin, although this one isn't really centered at the origin. These are just the vertices of a basic unit square with one of its corners at the origin. But actually, your motif should be centered at the origin. And there's a couple of commands: video writer, specify the video file, and open the file. You don't have to worry about those. That's just the necessary setup to produce the video file. So this program is going to run and then leave a video file in the working directory, which can then play just using the normal operating system video player. And then there's some initial setup of the figure window that's going to hold the frames. The only thing you might need to change here is these limits. So at the moment it's set that the x and y coordinates of the figure window go from -15 to 15. Depending on how big you make your motif and what exact translations you use, you may need to adjust those limits just so that your figure window actually contains the wallpaper you're producing. Okay. So those limits there should be more or less match the limits of your wallpaper project. Or for this orbiting example I do, those limits should more or less just capture, sorry, I can't see that, more or less just capture the orbiting motif around this. Then there's the main animation loop. So this is a loop which goes, so you can think of t as the time variable, say for the animation. So this is t going from 0 to 20, and it goes up in increments of dt. dt is set up here to be 1/30. So now I don't know exactly how the video file works, whether this will be 20 seconds long, 30 frames per second or something, but just think of it roughly as t is the time variable, and dt is the small increment in time between each frame of the animation. So then, here is where the main, so this is the wallpaper example. So this set of commands here, so here we form 3 matrices A, B, C. Now at the moment in the skeleton code, they just produce identity matrices, so they won't do anything. When we get these matrices and we multiply, you see here, we multiply the original motif coordinates by these transformation matrices to get what I've called their plotting coordinates. So these are going to be the coordinates of the new version of the motif, which has been moved somewhere in your picture, rotated, maybe scaled. So you'll have to change this part of the program. So you want to define A, B, C, maybe some more, maybe fewer than 3, as the appropriate transformation matrices. But you'll form them by calling the transformation matrix subfunctions at the bottom, which I showed you a few moments ago. Okay. You'll see that in the example I'm going to use. Then this fill command, once you transform the basic motif coordinates to the plotting coordinates for new motif, this fill command here will add it to the figure window. But now for the wallpaper example, these commands where you transform the motif coordinates and do the fill to actually plot the new motif, they'll have to be inside some kind of for loops to produce the what did I say, 6x6 grid, to produce these 64 things, sorry, 36 things, to produce the 36 motifs in your wallpaper pattern. Okay? So those commands, you'll need some kind of for loop or nested for loops to scan across the 6x6 grid to produce the new motifs. Then these 2 commands, you probably leave those alone. Frame equals get frame and write to video view frame. That takes the finished frame window, which is the completed frame for that frame of the animation, and it writes it to the video file. Okay. There's actually something missing there. We should end by close the video file just to terminate it nicely. It'll probably do it itself, just in case it doesn't. So that's it. So that's the basic skeleton of the wallpaper function. Now I've got a very similar looking skeleton here for my orbiting motif patch. So let's start completing this. So first of all, I'm going to, so the structure here is quite similar. So the motif coordinates, originally it's just a simple square centered at the origin, but I want to make this be my kind of diamond shape. So each column each column of this array holds the homogeneous coordinates of the vertex of this shape I'm going to do. So reading across the top row should be 3, 1, 0, -1, -3, -1, 0, and 1. That's the first row. Should be 2 3s. Yeah, 2 3s. And then the next row is all the y coordinates. So 0, 1, 3, 1, 0, -1, -3, -1. Those, all the x coordinates, the corresponding y coordinates of the vertices, and then the third row is just the homogeneous coordinates. We set that to 1 for each point, and there's eight vertices. We need 8 ones here. There's already 4 there, so I'll put them in 4. 1, 2, 4. So that array there is the array of homogeneous coordinates of the vertices of this star kind of shape. Okay. We got those commands to initialize the video file, so we'll leave that as alone. We've got these axis limits here, so I may need to go and adjust those later on. Well, yeah, now let's jump down to these. Okay, so I'm actually giving you some stuff for free here in your assignment. We want to complete these functions now to give us the appropriate transformation matrix. So this R that's defined in this function here, this should be the 3 by 3 rotation matrix by theta radians around the origin, anti-clockwise in homogeneous coordinates. Okay. So we discussed that last week in the notes. It's the cos theta, sine theta kind of matrix. So this it's going to be a 3 by 3 matrix. So this is on page 29 of the notes. So it's cosine. Theta is the input variable, so we use theta in the definition of the function. So it's theta minus sine theta, and then 0, so that's the top row. Second row is sine theta, cosine theta, 0, and the third row is 0, 0, 1. Okay, so that's the rotation matrix on page 29 of the notes. Then a translation matrix. So T, the matrix that this function T returns, should be the translation matrix translating by the vector xy. So x is the x component of the translation vector and y is the y component. So that's defined at the bottom of page 28. So again, it's a 3 by 3 matrix using homogeneous coordinates. So the top row is 1, 0, x, the middle row is 0, 1, y. And the third row is 0, 0, 1 again. It's going to leave the third homogeneous coordinate of 1 unchanged. And then we want a scaling matrix. So this matrix S that this function returns is going to scale about the origin. And you scale about the origin by a scaling factor R by simply multiplying each coordinate, multiplying the x and y coordinates by r. So again, this is just repeating the scaling matrix from page 29. So it's a diagonal matrix with r, r, and 1 on the main diagonal. So the effect of having r in the first two positions along the diagonal is to scale by r, by a scaling factor r in the x direction and a scaling factor r in the y direction as well. Okay. Now the advantage of using sub-functions like this is now we don't have to put these matrix definitions in our main script file. It'll make the main script file easier to use. Because now when I want to form a rotation matrix, when I want to use a certain rotation matrix in my main program, I simply use the command plot matrix theta. It's a much more meaningful instruction to have in the middle of your program than set R equal to this matrix with loads of sines and cosines. It's a lot easier to read, and it's a lot easier to do the program. Okay? So once and for all, we write the definition of a rotation matrix in a subfunction. And for every subsequent occasion, we simply use the much more meaningful command plot matrix theta, where we replace theta with whatever angle we want. Similarly, for translation matrix and scaling matrix, I don't want to litter my code with all these long, detailed 3 by 3 matrix definitions. I'd much rather use the more meaningful functions, transmatrix and scale matrix. Okay. So now, if I've made any errors there, we'll discover them because my animation will look wonky. And so we may have to go back and correct some errors there if I do. That's the thing with programming as well, that, you know, things never work first time. There's always a bit of debugging to do and correction and so on. Okay, so now we can start thinking about producing our animation. So here's my main for loop within the animation. So we think of this t variable as the time, and it's going up in small increments, 1/30th each time, from 0 to 20. So that'll be, how many frames will that be? 20 times 30, 600 frames. Presumably you'll play them fairly fast, quite a few frames per second. So we should have a nice smooth animation. If it's lasting too long, we can shrink this number 20. If it just executes too fast and we're not seeing enough of it, we can replace the 20 by something much larger. Okay? So we can adjust the length of the animation. So first of all, I want to do some complicated behavior here, but first of all, I'll just get the motif to orbit around. I'll forget about rotating it around its own center or getting it to pulse. Let's just make it rotate smoothly around the circle. So that means in the so I'll leave A and B as, well, let's delete all of these for the moment. So we're inside the T for loop. So we're producing a single frame of the animation. Now, if I just left this command here as it was, I just had the very boring animation with just the motif centered at the origin, and it wouldn't be moving. So it would last an animation 20 seconds long or whatever, with just the frame sitting at the origin. Okay, so we want to make it move around a little bit. So I want to take a transformation matrix. It knows that I've defined function there. So I want to use T to be trans matrix, and I need to give it two inputs. I need to give it an X input and a Y input. So these are going to be the X and Y components of the translation vector. Now I want to take it, the motif I've defined is centered at the origin, but I want to send it out to the correct point on the orbital circle. So I can use cosine and sine of the T variable. But those are the coordinates on a circle. If I go here cosine of T, and then here do sine of T, that will translate it to a point on the unit circle. Now, I want to send it a little bit more away from the origin. So I've already defined, like my thing has radius 3. Remember, some of the vertices were at position 3 along the axes. So maybe I want to send it further away from the origin. So we've got an appreciable circle that is going to move around it. So I'll send it out to the circle of radius 10. So I'll just simply multiply both these coordinates by 10. And then my plotting coordinates for this frame will be T multiplied by the motif coordinates. Okay. T multiplied by motif. So inside this for loop, each time it comes into the for loop, it defines a translation matrix, which will translate out to this point on the circle of radius 10. And I apply that to motif coordinates. So motif coordinates is this array up here, which is holding all the vertices of my basic shape. But when I multiply it by T, it moves all the coordinates, translates them out so that now, originally they were all centered at the origin. Now they're going to be centered around this point, which is on the circumference of the circle of radius 10. So I think I can go ahead and save that. And so I've saved that now, and it's called, what's the function called? The function is called orbiting example. So if I run the command orbiting example, that will execute. Yay. Okay, so we're actually seeing each of the successive frames being drawn. Now it will look a bit stuttery. It mightn't play that smoothly because this is using the virtual computer through the browser. So it mightn't look that smooth, but we can play the final animation file just on this computer itself shortly, so it'll look a lot smoother. Okay, it's ended because I'm back to the cursor in the command window. If I switch to using this actual computer sitting here in this room, I can see that same file in my documents folder. So we can have another look at it. So this orbiting ABI, see the timestamp 1557, so that was, the clock's a bit slow. Oh, it's this one. Sorry, it's orbiting example ABI 1603. So that file was produced just now. That was the file that the MATLAB program produced. So there's the nice smooth animation. Okay. So each frame of that, we produced each frame of that. There's a number of frames happening every second. We produced each frame of that by using our translation matrix function. Originally, the basic motif was centered at the origin, in the middle of this thing. And each frame, we used a certain translation matrix which sent it out to a point, to be centered around a point on the circle. Okay. Let's go back to our MATLAB. So any questions just about that at the moment, or how that was produced? Okay. So the structure of the program is this. There's this for loop. And the variable in the for loop is t. T is running from 0 to 20. You can think of that as seconds. It's not going to be seconds exactly, but think of that as seconds. And dt is the small increment in time between each frame. So at the moment, we're using 30th of a second. So within this t loop, I produce each frame of the animation. I'm doing it simply here. I use just a single transformation matrix, which is a translation. This translates to 10 cosine t, 10 sine of t. So that's the point on the circle of radius t. And as t goes from 0, so how many times did I go around the circle? See, as t goes from 0 to 20, I'm taking cosine of t. So as you go from t equals 0 to t equals 2 pi, that's one complete orbit, isn't it? From an angle of 0 all the way around to an angle of 2 pi. So 2 pi is a bit more than 6. So it went approximately 3 times round, okay? Because 20 is approximately 6 times pi. Yeah, so my thing went around approximately 3 times. Okay, but now let's get it to do a bit more. Let's get it to be rotating around its own center. So as well as orbiting around, it's going to be rotating around. So how are we going to do that? At our disposal, we've got this function down the bottom, which returns a rotation matrix for rotating the plane around the origin. So obviously, to get it to rotate around and to get it to orbit around the circle, I want to rotate the motif and translate. But the question is, in what order do I do that? Do I send it out to the point on the orbit first and then rotate the plane around the center? Well, no, because that will send the thing around the center, whereas it should be just out at that point on the circumference. Because if I do them in the opposite order, if I rotate the plane first around the center, that will take the basic motif and rotate it slightly. And then I translate it out to the appropriate point on the orbital circle. Okay. So I'll use a rot matrix command here. Once you've saved the M file, MATLAB knows you can do the tab completion, and it will complete the name of the function that you have there. I'm going to do rot matrix, so I want to rotate by some angle. What angle will I rotate by? Any suggestions? What kind of answer am I expecting from you? Remember, we're inside the for loop, which is using the index variable t. This is like the time stamp of the frame. So the rotation angle is to be some kind of function of t. Will we make it rotate really fast or really slow? Maybe let's make it rotate a bit fast. So let's do it 5 times t. Let's try this. So how does that work? And so this is going to give me within this t loop, R now is going to be a rotation matrix for rotating the plane about the origin by an angle of 5t. And here the order is crucial. I want to rotate the motif coordinates first and then translate. So in this command, which forms the plotting coordinates, I first multiply the motif coordinates by the rotation matrix, and then only then multiply by the translation matrix, which sends it out to the correct point on the orbital path. So maybe this will work. So save that, go back to the command window and run orbiting example. I'll run that. Something went wrong because it didn't, got me. I've got an error message. Let's look at our error messages. Now, I know lots of students get completely freaked out when the red error messages come up. They're there to be read and understood. So what's it saying? Permission denied, error in orbiting exam, permission denied. So it tried to do the command where it tried to access the video file API. So it said permission denied because I've still got it open in the computer. It's still open in Windows Media Player. So yeah, so that's a sensible thing to do. It doesn't want to deal with the video file while another application has it open. Because when you open a file, it creates a little lock file that prevents other applications look for before they try and change a file. So okay, so I closed down the Windows Media Player, so now it should let me run orbiting example. Okay, there we go. Now it looks a bit choppy. It's, again, that's, and it's outputting all the rotation matrices as it produces them. I'll put the semicolons in there too. But yeah, you can see flashing up here, you've got R and T matrices, and they've got entries which are rapidly changing. So those are the rotation matrices that it's producing as it goes. Back to the command window cursor, so it stopped. Let's just go back and look at the finished video file now. 1610 orbital API, so it's this one here. That's a nice smooth one there. So it's rotating around, and it's rotating around its own center. It's orbiting around and rotating around its own center. And you can see the effect of the 5t. So the 5 times t is what's making it complete many rotations around its own center in the time it takes to do one orbit. Because the orbit is tracking the angle t, whereas the rotation around its own center is using the angle 5 times t. So that will go through many periods. The rotation around its own center will go through many periods before you've gone through one orbital period. Everybody like that? You'll start to get a feeling how you'll be producing the wallpaper example. Something I can see kind of 2 images. It's kind of, yeah. I can hypnotize myself looking at that. All right. We'll get it to change. Maybe we should get it to change color as well. Now, what haven't we done? We've suggest no. Get sounds and colors into it as well. Okay. Now let's get it to pulse a bit. Okay, because for the full requirements on your homework, I want you to get the thing pulsing. So the pulsing can be achieved using a scaling matrix. So let's go back to our code window. Let's stretch it open again. I'll just add in the semicolons. I maybe don't want to see the matrices. I mean, it's useful to see them being produced. So if I add semicolons to those commands within the T loop, that will stop it printing out the transformation matrix. Well, it's kind of useful. It's kind of interesting to see. So now I want to scale as well. So within the T loop, I'll use the scale matrix command. Give me a scaling matrix. Well, think about the effect. As the thing is going around, I just want it to smoothly expand and shrink. Now, how are we going to get that? Do I want it to expand? It'll only have to expand out to a certain level. and then shrink back. Maybe I wanted to shrink to nothing, to just shrink to a dot, or maybe I just wanted to shrink just to some slightly smaller size. Let's think about making it go between double its size and half of its size. So what we want is this scaling factor to be somewhere between a half and, or let's say between a half and 1.5. So at its maximum, it will be scaled to 150% of its original size. It'll be half as big again. And at its smallest, it'll be half of its original size. So what we want is some expression. And again, it has, like the other ones, they have to depend on the loop variable t. Because t is the thing that's changing. So I want some function of t here. And I don't just want it to do it random changing size. I want it just to smoothly go in and out. So what kind of smooth functions would we know about that would go between 1.5 and 0.5? What kind of what will do the job for us? That will go between smoothly, starting off at 1. So I want a function which starts off at 1. What I want from you is so this is the scaling factor. Scaling factor on the vertical axis, time on the horizontal axis. So I want something that's going to smoothly vary between the axis down here. So between 1 and 0, sorry, what did I say? 1.5 and 0.5. You can start to see. Smoothly, so this scaling factor is going to smoothly vary between 0.5 and 1.5. It's going to start off at 1. So what function have I drawn there? I mean, it's some kind of cosine, isn't it? Or sine. I want it to be, if I make it to be, let's make the scaling factor r, and I'll define here little r. It's 1 plus sine, basically 1 plus sine of t, but the sine, what's the amplitude there? The amplitude is just 1. Now normal sine has an amplitude of 2. So it varies between +1 and -1. Normal sine has an amplitude of 2. I just want something there with an amplitude of 1. So I'll take a half times sine. If I make the scaling factor little r be 1 plus a half times sine of t. So that defines the scaling factor little r, and then I grab the scale matrix R. That gives me matrix S. Now, when do I do the S? Well, I should do it, you see, the T translation should always happen last, because that's the thing that sends the motif out to the appropriate point on the orbital path. So the rotation and the scaling, actually the rotation and the scaling are actually commutative with each other. If you rotate first and then rotate about the origin and then scale about the origin, or you scale about the origin and then rotate about the origin, those two operations actually commute. That's a special case. In general, transformations don't commute, but those ones do. So as long as I do the T last, I can do the R and S in any order. It doesn't matter too much. So now this time, now what happens at each frame is we grab a translation matrix, we grab a rotation matrix, we grab a scaling matrix, and we scale, rotate, and translate the original basic motif coordinates to send it out to the correct point and get it to animate around. Okay. Let's save it. Video file isn't open. Any questions first before I run it, or? An example, I probably should put a back and say function. Ooh, yeah, this looks right. So it's doing the right thing. Maybe, see, because I use sine of t, it's only going through one period of its pulsation in one period of its orbit. Maybe I'd like it to go a bit faster. We could make it go slower, but so instead of sine of t, maybe let's do 7 times t. Things go a bit crazy. Okay, so the 7 times t means it's pulsating faster. If I had something less than 1 times t within the sine, it would make it go much slower than the orbital period. Let's look at this full screen finished version. Okay, but you can see, you can appreciate the low level that we're doing this on. We're just starting with a basic motif, and we're carrying out all the necessary transformations ourselves. And you can also appreciate that, let's say you took the time to design a very ornate motif or an actual actual cartoon drawing of something, so a very detailed motif. All you need to do is just slot in those vertices. You'd have maybe hundreds and hundreds of vertices, make a very complicated polygon, a very detailed polygon. You just slot that into this program and just leave everything else the same. And those same commands would orbit and rotate and pulsate that complicated shape around the center in the same way. Yeah. So it's very, flexible approach. If you replace the original array of motif coordinates with something more complicated, more interesting, then that will do the same thing to that. Okay. Okay. Any queries or requests for clarification about the operation of the program itself or how it's working? Does the wallpaper one seem a bit more approachable now? Yeah, yeah. And of course, the wallpaper, the one aspect I haven't addressed is doing the 6x6 grid. So that's something I'd like you to think about how you're going to do it. Now, try and think of doing it in a nice, good programming style. So, one way to do it would be to copy and paste this block of code 36 times in the middle of your T loop. So one little block of code to produce each of the parts of the wallpaper in the 6x6 grid. But that's not good style. Yeah. So you're taking one set of commands, copy and pasting it 36 times in the middle of your code. Surely there's a better way to do that. Because then that's like doing the thing by hand. So it's rather think about inside. So this for loop, the T for loop is one frame of your animation. So within each frame, what you really want is some operation that's going to go produce, scan across the wallpaper pattern and drop each motif in the correct position, 36 of them, into the correct positions, and then finish. So you want some kind of operation. Now, how are you going to get something that's going to scan across positions like that? Well, a couple of for loops. For loop scans through a number of values in one dimension, if you like. If you put one for loop inside another, you'll have an outer for loop scanning across, say, but then the inner for loop can scan up. So you scan up, and then the outer for loop moves it on one. Then you go into the inner for loop and scan up, then the outer for loop moves it across one. So you can scan across your 6x6 grid using for loops. And then you keep this kind of basic block of commands as more or less the same, but just position for loops around them to get the same effect. Any queries? You can see the advantage as well of using subfunctions. So because I wrote the transformation matrix subfunctions at the bottom, it means my code is a lot easier to read and it's a lot nicer. If I hadn't written those subfunctions, in the middle of my for loop here, I'd have to have those big matrix definitions, which aren't as, it's not as clear looking at them what they mean. It's a lot easier to see, trans matrix is a translation matrix, rot matrix is a rotation matrix, scal matrix is a scaling matrix. So you use meaningful names for the functions and then use those within your main program. It makes the code easier to write because I just wrote those matrix definitions once, and then I was able to reuse them within the main program. Okay? It makes it easier to write and easier for someone else to read. And so. Okay, but all the framework is there for you, all the details about producing, setting up the video file, grabbing the frames, writing to the video file, that's already there. Because that's the, details around the edges, so to speak. Okay, so any further questions? Okay, well, maybe at the moment, do you want to work on some of these examples, or maybe even work on the assignment problems themselves? I'll go around, maybe I'll do a bit of workshop style. We don't have that much time left, but I'll go around and answer any individual questions you might have, individual questions or queries.